This video to prove to you the two equations we're going to be using for mirrors and lenses. And again, when we do this, we're thinking of this as almost the curvature of the mirror is very small, okay? Because we're going to see that we're kind of like going to need that for the proofs. Okay, so the first one is I already drew the rays so that I don't waste time while I'm doing the video. And you can see that this angle here is the same as this angle because I'm sending a ray from, or a ray is generating from the tip of here. It's hitting the mirror. I explained in the previous video that the tangent here is perpendicular to the principal axis, so you're going to bounce back with the same angle. Okay. Now, the distance from the object, this is the object, this is the image, the distance from the object all the way to the mirror, okay? Now, I'm assuming that the curvature is very small so that we're going to ignore this little extra. Okay, this is DO, and from here, the image to the mirror is DI, okay? Which basically is this distance here, kind of. Okay, that's DI. So if I'm looking inside this upper triangle here, okay, so let me just label it O, I guess B, okay, and this triangle is going to be I don't know, C, I guess. Okay, so if I'm working inside those two triangles, you can see that they are similar triangles. This is 90, this is 90. This angle is the same as this angle. So I can do proportions. So I can say HO over this length over the whole thing, which is DO, equals this height over DI. Okay? Now, which means HI over HO, which is basically the magnification, that's basically describing the size of the image compared to the object, is equal to DI over DO. And I'm going to come back and change this a little bit later. I'm going to add a sign to it. So HI over HO equals DI over DO. Okay. So that's one formula. Now the other one is if we look at this angle, it's the same as this angle. Those are vertical angles. Okay. Okay, so I'm going to work inside this triangle here if I extend it to here. That's why I wanted to make this curvature very small. So just assume that this point reaches there. If the curvature is very small, that's a good approximation. All right, so I'm going to say that this height, HI, over this distance from F to the mirror, which is the focal distance, is equal to, now I'm going to go to this angle and do the same thing, is equal to HO over this distance, which is basically DO, which is the whole thing, minus this F. I hope you can see that. So from here to here, inside this triangle, OAF, basically, okay? This distance here, OF, is from O to B, minus from F to B, which is little f. So I'm going to try to write that. So it's HO over DO minus F. Now I'm going to replace this HI and HO with the DI and DO. So I'm going to write it like this. Let's try HI over HO equals F over DO minus F. And I'm going to change this HI and HO to say DI and DO, right? And then maybe I'll just make this flat. So it's DI DO minus DI times F equals DO times F. And then at the same time, I'm going to move this to the other side. I'm going to add it. And I'm going to put F as a factor, right? And I'm going to move this around. So I'm going to move this to here and I'm going to make this 1 over f. Okay, so see what we're looking at now. So I'm going to take it up here. So 1 over f is equal to, now if I divide, I make two fractions out of this, it looks like it's 1 over di plus 1 over do. So this is going to apply to lenses and to mirrors. It's a simple proof, just using similar triangles in geometry. Now, I'm going to go back to this formula from earlier. The magnification is comparing the height of the image to the height of the object. Now, if you look at the object here, the image, it's flipped compared to this. Okay, so when you look at your notes, you're going to see that there is a minus here. And that takes care of the fact that it's flipped. Now, if it's upright, what's going to happen is di will be negative. So you put a negative there and negative there, the magnification will be positive. So that negative there takes care of that problem. Okay, and that's it.